So I'm giving an inverted talk. Basically, I will focus on the questions to answer partially the questions, and then give you the motivation. Basically, talk about experiments and why and theory is relevant. This was the questions that we were assigned. I'll try to address these ones and this one. We're asked to come here with a mission. So can we extract electronic correlations from optical correlations? So I just directly dive into this problem. And this is the paper that I have on the archive. And there are two other talks. One we already heard about, and the other talks, I think it's in the afternoon. This was led by my graduate student, and postdoc, Andre Grank. It was a long work. This is actually a very long paper. Very bad for the referee. Go through all that. So I start with photonic correlation functions. It's a mixed audience, so I thought it might be a good refresher what the photonic correlation functions are and how we can measure them. So the first one is intensity. So the A is the annihilation of a photon, and A dagger creation of it. So think about Fermi-Golden's rule that I have some matter that can absorb light and generate something like electric, like a photocurrent, or a two-level system that absorbs light. It generates, and I can measure it electrically. So then I can absorb a photon, go to some excited state, and then from the excited state I can go back. This is second-order perturbation theory or Fermi-Golden rule, and that's how actually Glauber told everyone how to think about photo detections. So basically, at a specific time, if that I can think of the rate at which that I'm exciting this photodetector, and the current that is generated would be proportional to this. So if I sum over F, then I'm basically measuring this quantity. This is basically the intensity at some specific. Of course, there are details to that, how fast this detector will be replenished, there is the dead time, etc. That would set the bandwidth and all the details. It depends if it's a superconducting photodetector, if it's a semiconductor detector, etc. But that's pretty much it. This is equal time. I can also measure one of them being at 0 and one of them being tau by interfering the signal with itself and then measuring it. I have not shown that on the slide. But basically, they don't have to be equal. I can also measure the coincidences. So I can split the light now over here, and then look at the coincidences. If I have a click on detector 1 and a click on detector 2 with some time delay. So the rate at which I will look at the coincidences mathematically is given by this expression. Again, think of it as Fermi-Golden, that I have some F over here, so I detect 2 photons, and then what's the rate associated? That's pretty much it. This is called a G2 correlation function, and it allows me to measure it. Now, what is a quadrature measurement? So now I'm interested in measuring just one of these guys. Of course, this is a phase-sensitive measurement because the phase in general is not well defined. We have to assume that there is a local oscillator, and then here is a local oscillator. So the scatter light comes in, I interfere it with some local oscillator. The beam splitter would mix these two. So now, instead of measuring A dagger A, I'm measuring A dagger that is mixed by some mean field. So the mean field is just a complex number, so I can just get rid of it, and I can measure the quadrature. Now I can even go further. I can measure similar to the G2. I can mix actually the quadrature and the G2 and measure these kind of correlators. So this is a quadrature, but the correlation between two different quadratures, but even delayed with time. So what you do is that you have your light, you split it in 2 parts, and then you do homodyne, basically dual homodyne measurement using the same local oscillator. And that allows us to measure. That's basically the very quick introduction to the correlators that we have. We can be fancier. We can post-select, and then you have multiple detectors, do G3 or Herald with one, measure the quadrature double, all those ones. And then the goal here is that I have these light correlators. I want to relate them to matter. I like to create this dictionary. Okay. So now it's tempting to basically relate some matter operator to each of these photon operators. So this is my correlated matter. The light comes in, and each A would be associated to some matter correlated, and then I measure them over there. So it would be one-to-one correspondence. It's like that, but it's a little bit more complicated. So why it's complicated? I can explain it in a two-level system. I love two-level systems because they're simple and easy to understand. So let's go to the G2 correlation function of a two-level system. It cannot get easier than that. So I have a two-level system. I excite it weakly with the field. This weak is important. So most of the time, the atom is not even excited. But once it's excited, it can emit only one photon at a time. And that time is 1 over the decay rate of this. So I collect it, I send it on a beam splitter, and then I do this coincidence measure. Of course, this is one photon at a time, so the coincidences should be 0. It's impossible for this atom to emit 2 photons at a time. It will emit 1 photon at a time. So certainly at the G2 of tau, G2 of tau equals 0, I should see anti-bunching. The photons are anti-bunched, not coming at the same time. But if I wait long enough, then I will recover, and then if it is driven by a classical field Poisson distribution, then I would get 1. Basically. But this is not the case if I put a filter inside, in front of one of my detectors, like a frequency filter. Well, the frequency filter, I can think of it like a cavity. The light comes in and spends a lot of time inside the cavity before it goes to the photodetector. What does that mean? It means that I can store my photon for a long time so that anti-bunching behavior is completely gone. And this was known around the time I was born, but kind of known to the experts, not known to the experts, etc. But there are recent papers, experimental papers, to show and appreciate actually this subtlety. Basically, G2 is in the eyes of the beholder. It's not just a thing that I go and measure. So the two-level system picture of it, put forward by Jean Dalibard, is that the two-photon process, there are 2 types of them. One is the double Rayleigh scattering. So I absorb a photon and I emit a photon. I absorb another photon and I emit a photon. Both of the photons are emitted at the frequency of the laser. So then this is the middle peak. Or I can absorb a photon, go to some virtual state, absorb the second photon, and then emit the second photon. Then during this process, I will emit a photon equal to the omega L plus the detuning. So this is this peak. And then this one, this is omega L minus delta, because the sum of them, of course, should add up to 2 omega L's. The input energy should be equal to the output energy. It's quite simple to do. So now, this picture I said is that if I filter one of these peaks, then certainly the anti-bunching is gone, because the anti-bunching is the interference of these 2. So I have to, if I resolve it in time like this, the anti-bunching can be seen. But if I resolve it in frequency, the anti-bunching is gone. Yes.
This is related to Mahler triplet, right?
So I talked to John actually. So so the Mahler triplet is when it's strongly driven.
Yeah. So what I'm saying is, like, if you just drive it weakly.
Yeah. So Mahler triplet, the definition is that if I strongly drive it, then I see Mahler triplet. But this is like a 2-photon scattering. But kind of this is a reminiscent of that Mahler triplet at the big drive limit. In the quantum optics books, you don't see this derivation. You just have a master equation that applies to Mahler triplet all the way to the weak one. But and then you do quantum regression theorem and calculate your G2 correlation function. But when we are looking at low scatter light and we want to relate it to the many body correlated systems and then see what on-to photon, etc., asymmetric formalism is, this is actually the starting point. Master equation cannot be the starting. That was the key. Actually, for me, for us, it took a while to set it up because the quantum optics dogma would be that you go to the master equation into quantum regression theorem and then you have your correlation function. That doesn't. So with that filtering in mind, then the dictionary will be a little bit complicated because for each of them, for each of these A, I have a matter operator, but they're convoluted with some filter function that I just introduced in the last slide. So it looks complicated, but if you see, I have a one-to-one correspondence between A and M, but then now for each AM, I have a filter function because we have this filter. If you put the filter, if you don't put the filter, it matters. And we'll say why it matters. So there is a list of them. So the rest is that we have to first specify what is our underlying Hamiltonian for the matter. And then work out some of these operators such that it is useful. Okay, so the easiest or the best model is the Fermi-Hubbard model at half filling. It's great. Why at half filling? Because I can relate the light matter coupling to the spin operators. So how is it done? So Fermi-Hubbard model at half filling, you have the spin sector. And then you can have the one excitation sector, which is the one Holland and one double, they can pair or not pair, or I can have two of them. And each of them, let's assume that they're separated by some large energy scale U. So the way that we incorporate the interaction with light is through Hahn substitution. So when the atom is hopping, it can hop just electronically, but also it can absorb or emit light while it's hopping. So basically the dipole associated to this transition is the electron going from one side to another side and back and forth. So I can do that. I can absorb a photon and emit a photon. Then I come back to the spin sector. But by doing that, I've done something with my spins, and then this is just S dot S. And it's very simple to understand because if I'm not in the singlet state, I cannot do this process. If I'm like this or I'm like this, I cannot do it. But if I'm in the singlet state, because of the symmetrization, I can do that. So that's pretty much what it is. So now, what are the processes? So the two-level system is actually a good guiding principle because this is now, instead of having two levels, we have many states now. So we can do double Rayleigh scattering. So we can absorb two photons and emit two photons while remaining in the spin sector. In contrast to the two-level system, I have to come back to the same ground state. But here I can go to some auxiliary spin state and then do another one. So even that is non-trivial. Even double Rayleigh in this situation is not trivial. And you see, I emit my photons, both of them at omega L. Now, I can also do this virtual transition as Jean Dalibar's paper, and then emit a photon which is equal to this gap U, and then the other one which is 2 omega L minus U. So this is this one, and then this one will be the here, or I can do double excitations like this or like. So during these processes, I'm basically, my photon is inheriting these matter operator, A operator, B operator, and then C operator. So the A operator is the one that I just introduced in the previous slide because it doesn't happen if I'm not in the singlet state. So it's just the SS minus 1. And then this B and C that are centered around these frequencies tell me about some mixed spin charge operator. remember this test was nice because it was always in the spin sector. I just virtually go to some excited state. So I create electron hole pair and then plug it back. But then over here, I create something over here, and then I'm on shell. So I've created actually a double and a hole on, and it can propagate. Here it's also the same. But it's not just the spin, there is also some current associated.
Mohammed,
Yeah.
for all that work, you need to be in the weak light matter cavity?
Yes. So these are all perturbative in the fourth order in the field. So I missed the introduction. So this is basically the Raman formalism for that was put together by Shariman and Shastri many years ago, and then revisited after that company. So we are going to the next order with all these subtleties of. Okay, so so I'm not going to tell you what this A and B and C is because they're very big and take pages of slide. Just give you like 3 examples very pictorially how they may look like in some limits. So Heisenberg antiferromagnet. So now let's just focus on this A term. So the A term is like this. I can do both in Primakov and Polygov to just write S in terms of some bosonic operator. These are my magnons. So what happens is that I absorb a photon, I create pairs of magnons, and then I emit a light during this process. So what happens is that I can create a pair of magnons, I can destroy a pair of magnons, or I can just dispersively shift. So this doesn't change the number of them, but just change. If I'm doing just one photon scattering or intensity measurement, this doesn't matter. But when I'm doing 2 photon, it may matter. So what are the 2 photon processes? So the first photon is absorbed, created 2 magnons, and emit a photon. Now the second photon comes in. It can absorb, I can annihilate these 2 magnons and then create another photon. That would be these 2 photons are now correlated with each other. So this is kind of a cute signature. If someone could see it, that would be great. That it's like a 4-level atom process. That with one you create an excitation, and with the other one you undo it. And this really happens if I've created magnon. Then there are these other processes that we can keep the other magnons and then generate another pair, or you can generate another pair, but on top of those because they're bosons. So I can basically, where I can just measure the presence of the magnon with the other one. That is the dispersive one. So the second one is a spin chirality that I advertised to show, and this is motivated. It doesn't measure the spin liquid order because for that I really need to measure Wilson loop operators. But it's a signature of that was numerically suggested in this work, and then in this work it was worked out for the TMD. Was all whether one can see it. So with that, we were motivated to go after this S cross S, and indeed it breaks time reversal symmetry before Eugene catches me to point that. So it basically the system itself, the Hamiltonian, does not have time reversal symmetry, but it breaks it, and then this would be a good signature to see whether it has been broken. So how does this work? Why it should come out? I'm here looking at a triangular lattice, but I could have done also a square lattice. So the first photon comes in and then generates an electron hole pair or a double photon. And then the second photon is absorbed and then creates another one over here. Now, these guys can be recombine and emit photons independently, or they can recombine in the opposite direction. So basically, now this one and this one can recombine and emit a photon. So I have an emission of a photon from all being plugged on this side, and then the second one. So you see that I created this and this, then I plug them this and that. So it's like a ring exchange. So certainly it is measuring not just two independent links, but how these links are related to ring exchange operator. So this one can be measured in this G2 correlator, or one can actually look at the quadrature fluctuations, that is the double homodine that I mentioned. Because these are morally related to each other, either measuring the fluctuations of this or Heidegger is. Another one, another application 3 was motivated by a theory proposal by these folks. That were proposing a way to measure topological fractions. Detect topological fractions, not measure them, which is kind of my idea. So what's the idea? Imagine that during the absorption of my photon, I create a anion anti-anion. Think of toric code that I'm creating in ENM or some other things that I'm creating to anions, one third charge or one half charge. They can wander away and then they can come back, fuse, and then emit a photon like that. So I can excite these anions and I can detect them both. Now, imagine that during this process, I create another pair, another form of another pair. That this pair now can interfere with this path of fusing anions. So I have another light that is also creating. Now, if the path of these two anions that have been created and then fusing interferes with this, it messes up the interference pattern of the original one, and the optical field that I'm detecting over here will be affected. So that's pretty much it. So now I can call this pump and probe. Depending on the presence of this pump, I should be able to see something in the probe. I'm not measuring any fractional statistics. I'm just feeling the presence of them, because if it's a fraction, it should mess up the interference, and that's pretty much it. So that was for a pump probe that was classical, and it has its own problems because you're generating many of them, you heat the system, etc. Our contribution was very modest in this category. Is that to say that you can even do it at the single photon level. So if you just scatter 2 photons, you can get the same thing. You have the advantage of doing the post-selection, so you can herald the interference of these anions and the emission of the photons, etc., by doing this heralded system. So now that was my contribution to the panel, right? And then what are the other questions that are going is that so far we looked at the input field that was classical. Yes.
So the regards to those processes, particularly, I guess, when you were talking about these kind of quasi ring exchange, this in conventional language, this is simulated Raman, right? So, I'm not sure if you use the words, but I just want to make sure I understand.
Simulated Raman. No.
Don't have the anti-Stokes.
Yeah. There is so I'm so the field that I'm measuring is in vacuum to begin with. So the classical field is the Raman field. Sorry, the classical field is the input.
You have 2 photons in and one of them out. One of the photons in is a vacuum field.
Let me show you. So in the stimulated Raman, I have such a situation, is that you have this field, and then you measure what happens to this field. This is the stimulated Raman. Here I assume that this field in the beginning is in vacuum. Does that make sense?
When both fields are classical, right?
Yeah, that's right. So I have this field, and I will look at the gain or loss on this one, right? Either it's a Stoke or anti-Stoke. Here, it's a spontaneous. So this is in vacuum, and then the station of this can generate. Make sense? This is for this formalism. Now, does it have to be the case? That's my last slide. to measure some spin order. But in the G2, this has to be in vacuum to begin with. Otherwise, it's just fluctuations on some classical field, and that's basically not measurable. That's the usual situation. If you drive everything classically, then this G2 measurement is another question. Yeah. So our input field was classical. We can also have a squeeze light to come in, etc. For most of the cases, I don't think it's going to help. But for cases that we are talking about the quadrature measurement, it would help, because if we are doing quadrature measurement, then it's better that the input light also have squeezed quadrature. How to translate such formalism for real materials, in particular, what kind of materials can be described by this single band Fermi-Hubbard model, what happens to semiconductors, etc. That's the next part of the talk.
I think the first thing that you mentioned of using light quantum, what you will get that you will not get classically.
For example, for this S dot S cross S, it's very, it's possible to do it with higher order Raman transitions, but it's very messy, because here you can really be sure that the signal is measuring S dot S. Not impossible, but it's just super messy. So that's one example. So everything I presented in the first part of the talk, there was no momentum in it. So it was dipole approximation. We were not imparting any momentum, and we were not measuring any momentum. We know that it is possible to do this if we have a nanotip that we can do near field measurement and resolve momentum. That's a relevant theory question. This is one way. Maybe another way that it was done in our group is that we kind of give up on the ability to move the things such that we can do spatial tunability to some passive structure where the matter, the physics is made on top of a plasmonic structure. And then now out of this plasmonic structure, we measure. So we are kind of giving up on the tunability of it, but then the collection efficiency is quite good because we can put now detectors on this side or on that side, and then look at the photons that are coming from the material up to, again, the same situation, like maybe 100 nanometer to 50, if we really push it, maybe 30. That's another way of doing it. Can we extend these ideas to measure higher order correlation by going to the higher orders? The answer is yes, but it's difficult. This S dot S cross S, it took Gautam actually a long time to figure out which channels we have to do such that you only measure S dot S cross S and not other stuff. Entanglement, can you measure Rene entropy? I was sharing an office with Martin at KTP, chatting with some ideas, so I'm interested whether that's possible. And then what happens if I have a pure excitonic system? So here we were just thinking about, I have some electronic matter, I come with 1 or 2 photons to interrogate this electronic system. That was the question we were asking. Now, the relevant questions can be answered if I have a purely excitonic order. So my electrons are boring, but I've pumped a system with a bunch of excitons, similar to Anna's talk, that now these excitons are strongly interacting with each other. They form some interesting state, and I collect the emitted light in a smart way. Can I see something? In particular, we had some predictions that we can have bosonic fractional Chern insulator in these TMDs. it possible to collect the light and then prove that it is? In particular, we are thinking about measuring the edge of the system that has this chiral latitude. So that concluded my mission. Now I would like to go and motivate why these things are relevant to the experiments. How much time do I have to check?
A little 10 minutes.
10 minutes? Okay, I will be fast. But
11.
So one has to be realistic. That was really a theory work, and now one has to work out what's the relevance of it to an experiment. So one very nice platform, Hexagon in semiconductors, because we have a good understanding of the underlying Hamiltonian. So you have, imagine generically you have a bilayer in a Moiré system. So in the momentum space, you have the top layer and bottom layer, and then they play a super lattice for each other. So the bands will be split. So in space, I have generically this situation. So I have in position space, I have some potential. I can dope the system, I can put the electrons in the conduction band, they strongly interact with each other. And the game is that if I create an exciton on top of this correlated material, how this exciton moves in the system, should I think of it as a two-level system? This came up during Anna's talk, that is it like a bound state that is moving through this electronic state, or no? One has to be careful about this picture. And then what are the current operators that we can measure, like in magnetization, and whether we can drive the system and then engineer the Hamiltonian. That was the last mission. So these are the three works that I won't have time, but I will briefly tell you about. So this is a work that measures magnetization in a twisted bilayer tungsten selenide. To measure the quantum anomalous Hall states. So this was reported that this material could have a quantum anomalous Hall using a STM measurement, but there was no measurement of the magnetization. So here we are doing optical measurements, sigma plus, sigma minus, will have different responses to show that there is a magnetization. And then if we follow rest of formula, etc., we see that Chern insulator. This work is how to use the similar kind of math that we used in the first part to drive the system, not just measure that underlying Heisenberg model created by the electronic structure of the system, but optically implement or induce a Heisenberg model. And the last part is about the non-monogamous nature of these excitons. I said this exciton is not a bound state that is moving through the system. In contrary, all the electrons, let's say in the conduction band, they're equal to each other. So if you create an exciton on top of them, this hole does not have to be loyal to this specific electron that was coming from the photoexcitation. And then the dynamics is more complicated. So I said to appear in somewhere because I'm under embargo, so it will appear somewhere good, sometimes soon. Okay. So generically, you have you can create think of an exciton, electron, and hole pair across the layer. The advantage of these interlayer excitons is that they're long-lived. They can have like microsecond or a few microsecond lifetime, which is infinite for a material, and they have strong interaction. Both I'm talking about exciton-exciton interaction and electron interaction. So you can dope the system. That's why we call them a Bose-Fermi mixture, because we can change the population of the electrons independently and the population of the bosons, being the excitons, independently by pumping stronger or weaker. So when you create excitons, you have a bunch of electrons that are there over doping. You have this exciton that has some energy. But now if you want to create another exciton on top of another electron that is already there, the energy of these excitons will be shifted. or if that site was already occupied by another exciton, again, the energy of this exciton will be shifted. So there are two types of processes. One is this energy and the other one is this energy. And as I said, all of them are about tens of millieV, so that makes them experimentally observable. So this is one experiment. It was also observed in other groups. This is the doping in the conduction band. If there is no doping, my photon, an electron, and a hole will recombine at some specific frequency like this. But then if I dope the system, I put one electron per site, then when the electron and hole want to recombine, they come at the higher energy because the energy of this exciton was higher. You can also dope the system optically, meaning that you can put so many excitons in the system that if you want to create excitons on top of that, you have to pay. So in both cases, the energy price, is larger than any decoherence and dissipation rate in the system.
Do I have to worry about, like, let's say if we talk about exciton-electron interaction, will the electrons have opposite spin or the same spin? Because then interaction is probably very different.
Different. So here is just charge. So here, let's assume that I have n equals 1.
Right, but let's say if you already have an electron with this spin, you probably cannot make an exciton with the same spin by Pauli principle.
That's right.
Unless you go to a high band. So are you not allowing this?
I mean, of course, it's allowed. The short answer is that we still don't know. So we are doing actually experiments to see some spin physics using these methods. And it's complicated to interpret. Happy to sit down and talk. So I can specifically tell you in what experiments we are doing. So in this, one of the experiments is the following: that we look at the diffusion of the system, because diffusion is nice. We create these excitons over here, and then they diffuse. So we shine light at the laser spot that is shown in red, but then the PL comes at the wider one. So we can monitor this width to see how that changes as a function of different parameters that we change in our system, like the doping. So we can dope the conduction band. So this is the photoluminescence as a function of doping in the system. So here is 0 doping, no electrons on the conduction band. Here it's 1 electron per site over here, and then here is 2 electrons per site. We have to go to very, very low power to see some interesting signatures. This was not observed, or because one has to really go to damn low power. So immediately one sees the formation of the trion or polaron. So if there was no electron, I would just have an exciton. But if I have an extra electron, they can lower the energy, as you can see it shift and form a polaron. And if I put a lot of electrons over here, then the exciton, when I want to make it, it should have a dump that was related to this. So naively, if I had this idea that exciton is bound, and if it wants to move in the system, if I get to a Mott insulating state, if I put 1 electron per site, then the diffusion of this exciton should be suppressed, right? Because I'm getting close to an insulating state, but it's not. It's actually going up. So if we assign some diffusivity to this exciton, we see that it goes by 2 orders of magnitude. The reason is just as advertised in a couple of slides before, is that this hole does not have to remain loyal to that electron that came from the photon excitation. It can actually decouple from that electron and then moves by itself. So it would recover the diffusion of a bare hole. That's what we call non-monogamous exciton. And then, which I'm not sure whether it would come out in the print in the end. That was one of the issues with the referees, that we're coining a new term. Then the second one is the suppression of the Moiré lattice. So this is more like the details of the system, because this is the H stacking. So there is a hole between 2 electron sites. when you dope the system, it would reduce this barrier. So this is more details. And then the reason that why we saw it in the H stack and we didn't see it in the I stack. So and then we are doing the spin measurement of that since I don't have time left. 2 minutes, yeah, I know. I just mentioned briefly about this quantum anomalous Hall, is that the typical way for us to measure magnetization in this system is through this Flatiron spectroscopy that was pioneered in this paper. That if I create a Flatiron in one valley, the optical absorption of that depends on the population of the electrons or hole in the other valley. This is like very similar to this atomic ensemble enhancement. So the absorption is proportional to the population in the opposite valley. So by doing that, by looking at this attractive Flatiron and then resolving for sigma plus and sigma minus, we can measure the magnetization in the system, and that's how we could see this hysteresis. And then following Strato formula, measure the Chernobyl. Then we can see that as a function of displacement, the system goes from a ferromagnet to antiferromagnet as much as we can tell using Curie-Weiss law, basically fitting it to high temperature behavior. But all of this is measuring expectation value of sigma z, not even sigma x and sigma y. It's all sigma z. So it would be great if we can measure s dot s or sigma plus sigma minus expectation. So I take like 30 seconds to explain it because it kind of takes you back to the first part of the talk. It's basically inspired by that. Imagine that I have the valence band and a conduction band, and it's in say n equals 1 again. Now, if you shine light, you have AC star shift. This electron can be excited, or this hole can be excited and come back to its place if the polarization of the light is sigma plus. So remember, in this TMD systems, sigma plus talks to, let's say, spin up, sigma minus talks to spin down. Now, if I apply 2 photon transitions, now here this is a stimulated Raman. So both of these fields are classical. Then I go to some virtual state and then come down. And I make sure that the 2 photon detuning is exactly equal to the on-site interaction. Then I promote this kind of transitions. Or I can be off resonant with that, such that I can now go back, but in the opposite way. So now I have another pair of lasers that they talk to sigma minus, so they can tickle the spin down hole. And then instead of this red one going back to this side, the blue one can go back to the place. So I do a 4 photon transitions. And if this is off resonant, then it's basically my Heisenberg model. Fourth order, and then the ratio between these two and the phasing between them will determine this alpha. And by symmetry, you can argue there are no other terms. It's just the only terms that they can do up to some.
Don't you have a gauge dependence on those observables? The sense that this is you did in you took the Coulomb gauge to get here, but then if you have a spin orbiters x, y are not going to be good quantum numbers, and they will depend on which gauge you use. Maybe we can discuss.
These are gauge invariant.
The whole problem.
So we can drive this and then have a Heisenberg model, or we can probe them. So for example, going back to stimulated, we can have this is strong, this is strong, this is strong, and then this one weak, and then monitor the strength of that, whether we have a gain or loss. And that would probe basically different estimates. That would be great because now we can go back and differentiate with some of those.
That's a good question. like this SX term, it has S plus, S minus, right? And S plus means going to another value, which requires momentum. And it always sounds the light can give you such a large momentum.
So it's not on average. It's still I'm in the okay. I'm not going to be
They compensate.
Yeah.
So you're saying you're just borrowing it from Coulomb interaction somewhere.
Yes, and also the condition for this is written over here. Non-zero overlap with the overlapping sides. So I still need to impart some momentum to the hole to go from one moire cell to another moire cell. That is required, and I think with the edge stacking is kind of there because the electron resides between two holes. When I create an exciton, it can recombine either back to its spot or to the other side. But that's not the original lattice KK prime. This is the moire. So it's more forgiving. That's the key assumption of this. If it doesn't work, then our assumption was wrong. Yeah, but this is the key assumption. This overlapping with two tools. So I would like to also acknowledge now, since I managed to give the second part of the talk to the experimental group, because most of it was experiment. And then the theory group, the theory work that I just mentioned about the Heisenberg was led by experiment in collaboration with my colleague Yojo, and then the story of the diffusion was also collaboration with Michael Knapp.
Thank you for this both parts, and first part that was very tutorial. So I have a question about your lookup table. So great table. So is there other entries look a little scary to me? But are there any insights that in this table that we can only gain from going into this advanced measurements on the left hand side, or this information can be obtained in other ways?
Question. Knowledge. It's a hard question. So I can yes. As long as we are measuring something that is doesn't hit the nonlinearity of the system, I think all of them can be in principle be measured. But if it goes and measures the saturation of the system in some way, then it cannot be measured by just doing it. So for example, if I'm creating these magnons and they're non-interacting, etc., I think in the end, it would be just either intensity measurement or quadrature measurement that remains Gaussian operation. It only becomes interesting when the Wigner function of the photons becomes negative. And that's when the system imprints some interaction between those two photons. In the case of the two-level system, it's very simple to understand. The one photon will saturate this atom. The second photon will see a bleached. So in the many way, the system is not really the case because I have so many sites that I can excite at the same time. So looking at cases that can be probed by this negative Wigner function, it's particular. But that's like a very vague and general thing. For the specific answer was this S dot S cross S.
And this interesting slide showing connection between photons and Flory operators, right, for magnets. So if I understand correctly, you're saying that G1 is more or less equivalent to, let's say, calculating like a single correlate of Fleury operator, which of course we know because that's Raman scattering, so like there's a long history. But if we measure G2, you're saying this would be equivalent to computing nonlinear response, like two-dimensional spectroscopy for the Fleury operator.
Yes.
So if I know how to compute this spectroscopy for Fleury type operators, I can predict what G2 will be.
Okay, very good question. Very good question. How, in general, these G2 is related to pump probe experiments? Because you say that there is a huge literature of just doing classical pump probe or pump probe push experiment.
No, just like Fleury operator, right? They do linear response with that operator.
Yes,
And that explains like Raman scattering.
that's right. No,
That we know, but nonlinear response is less studied.
it is less understood. That is fine. I'm going one step ahead. Saying that the natural question to ask is that how these second order or higher order correlations that you're calculating are related to the usual pump probe experiment. It kind of goes back to Dimitri's question. In some cases, they're actually measuring the same thing, but in two different ways. For example, I can give like a simple example of Chi3, like optical nonlinearity in a system. So I can measure the Kern nonlinearity by just looking at how the intensity responds, how the system responds to the intensity change. I can also measure it using G2. So both of them will measure Chi3 response of the system, but in two different ways. Should I do G2 to measure Chi3? Probably not. I'm susceptible to degeneration if my photons will affect my underlying electronic system, then probably I should do G2 because I want to do a minimally invasive measure. But to find like an observable that is uniquely defined, uniquely measurable by this G2, one has to work out. I hope that's clear.
Yes, I don't want it to be exactly a connection between like one experimental measurement and another. But can you again just give me a table and give like if I can compute 4-point correlation function for Fleury operator, can I then express what you will measure with G2?
Yes.
Yes, it's a good point to stop. Thank the two speakers before lunch and